Morning, everyone.
So just so everybody knows, I'm recording everything Zoom sees, and I'll post it. I don't know if you all saw the link I sent, but I have a couple YouTube videos up now with these recorded sessions, and this one will be up soon too. No.
It's on.
Could you just change water really quick and clear that out for me? Just like dump the water out and refill this really quick. Okay. Um, looks like most everybody's here. Just waiting on a couple stragglers. Go ahead and get my tablet hooked up here and we'll get started. Hmm. Okay. Well, I suppose we can get started here. Just missing a couple people. Um, okay. Well, so same procedures last time. I'm recording this time the actual like Zoom screen, so you don't get to watch me just like doing a bunch of random stuff in the background on the video. Okay, so this time, same kind of structure though. I'm gonna pull up and share the document really quick, and then I'll talk about some of the theory here. I'll spend a little less time on this one since it's somewhat straightforward. Last lab, there's more stuff going on with this vector addition, more stuff to keep track of. Here, it's, well, this lab is a lot more setup oriented, and we're not doing a setup. So it's going to be probably a little shorter than the last time. Okay. Let's see. First of all, I'll go ahead and share the screen here. So this is the lab you should see. On the Blackboard link there, I have the PDF version if you want to look at that, but there's also the link to the Google the Google Drive, and there's also a doc, the .doc, which actually, I don't know, the .odt would be a little bit better, but so be it. Again, gives you a quick little introduction here, kind of a little more calculus heavy than it needs to be, but a little intro here on what we're doing. But essentially what we're going to do today is we mess with just values and units of values, right, with no dimensional quality to them, like no directional quality. And then we started talking about vectors having a value and a direction. And then now we're actually going to continue our thought of vectors and directions, but we're also going to apply some kinematics now. So kinematics is a very, like, I don't know, it's one of the hallmark physics concepts. It's just equations of motion, right? And that's what this is here. It's called equations of motion, because the thing is, last time I introduced rate times time equals your distance, things like that, just for a moment. But now we're actually going to use it and make some plots. Well, use some plots. Anyway, so this is what you should see here. A little theory. I'm going to go ahead and just switch over to my notes and then give you a little background. What's happening here. This whole procedure setup isn't really important because we're not really setting anything up. You can see what exactly we would do here. I can describe it, but basically, we're setting up a cart on a certain angle. It's on a track, and the track's kind of up at an angle. So there's a stand under one side keeping up with this constant angle. We put this little cart on the very end, and it has a measure for your velocity and your acceleration and distance traveled, and it records that information as you let go and let it just accelerate down the track. And you expect it to accelerate at a constant rate, starting from zero velocity, starting from position 0. So that's normally what we would have done had we actually been in the lab, but this time we're just going to go ahead and take the data that someone got from the actual lab itself, and then we're just looking at it here. So we're basically just going to look at a graph, look at some equation of that graph, equation of the slope and whatnot, and we're just going to take information from that, store it, and then work with it a little bit. There's only a few questions here. So that's kind of the background. Also, I want to say there is a typo right here. For everybody to look at this position versus time simulation, the first data. This right here, oops, this little x of t equals 0.8515 t. That t should actually be squared. So there should be a little tube above that t there, should be squared. All right? It's just a typo, just a missing value there. But yeah, so okay, so I'll switch over now to the stop the share here. Okay. Okay, so looks like everybody can see that. Good, it's recording. Okay, cool. So last time we talked about vectors for the first time in this lab. So before that, it was talking about just unit conversions. So yeah, we started with scalars, right? Just a value, no direction. Sloppy there. Then we moved on to working with vectors. Vectors just being a value in a certain direction. And we'll look at an example of that right now, just to clarify what we have here. We have vectors be value plus direction. So last time we worked with vector addition. This time we're actually going to work with the equations of motion. So we're going to use vectors in the sense that we're going to have a velocity pointing in a certain direction, and that's going to accelerate us in a certain direction, and we're going to have a change of position in that direction. Now, it doesn't really help us to talk about north and south, east, west in this situation. So what we do now to give a value a certain direction to make something a vector rather than a scalar in our examples, we're actually going to make everything pretty much on this XY coordinate grid, standard two-dimensional coordinate grid, where this is your positive X direction, your negative X direction, positive Y direction, negative Y direction. So you can say something has, you can give something a directional value here by saying, let's say, I can start it with a one-dimensional example, which might be a little better. So let's go ahead and start with a one-dimensional example. If I have just I can only travel in one dimension, right? So I'm going to have positive X, negative X. Going to the right is positive, going to the left is negative. So if I have something like my velocity is -6, in this situation, in this context, that means my velocity is pointing to the left at some point with a magnitude of 6. Okay. And then, if it was +6, then it would be pointing to the right with a magnitude of 6. Okay. So that's how we kind of retain our directional component to these things once we actually start working in the coordinate grid. It's easier to keep track of that way. Otherwise, north, south, east, west doesn't really make much sense. So we actually work with that here one-dimensionally. If you're going to do it in 2 dimensions, you'd actually have to add on the values that we used last time, these X hat, Y hat things. If I want to say my velocity was in the positive, where let's say I can say my velocity is something like 3 in the X hat direction minus 6 in the Y hat direction. So I can give myself a velocity vector like that. That's similar to last time we had these force vectors. I said something like F of A is, I forget what the numbers were, but something like, 20 in the X hat direction minus 36 in the Y hat direction, or whatever it is. Right. So this is kind of like that version, the same version of that. I want to mention this just because I want to mention velocity, and then kind of how we deal with direction of velocity from now on, basically, in these problems. We have the definitions here for speed and velocity. I want to make sure that we talk about just really quick. So speed would be something like that's 65 or 60 miles per hour, right? That's just the scalar. That's just it's a value for how fast you're going. But then velocity is going to be something like 60 miles per hour, north. Okay. Or in the positive X direction, or whatever it might be. So that's the distinction I want to make right there. And actually, I think it asks you something about that. And that's just so we've been kind of building up and talking about. So now I'm going to just mention it here. In the context of your actual motion through space, speed is a scalar and velocity is a vector. So what that means is you got to pay attention when they say some velocity is -5, that means it's usually 5 in the negative X direction. Okay, depending on what your one-dimensional value is. Usually in these problems, for now, we're actually going to have a two-dimensional problem eventually, but for now we're just doing one dimension, so all you care about is the negative positive means left or right. Okay, so basically, now what we're going to do is we're going to talk about kinematics. So kinematics is basically just a branch where we talk about the motion of particles through space, given some acceleration, some initial velocity. You know, if you know the initial velocity of something, you know it's accelerating at a certain rate, you're going to be able to figure out how far it goes in a certain amount of time, right? There's a set amount of equations that we use to actually make those calculations, and that's essentially what I'm going to give you now. The most important of which is this one above right here. So it can be delta x or delta y or delta whatever distance you want, but I put a big capital triangle like that. Delta x means change in x, which can be positive or negative, by the way, depending on how you set it up. You can have a negative change, means you go backwards, or you have a positive change, means you go forwards. Or if you're talking about your y direction, that's your vertical, then a positive delta x or delta y would be going up, and then a negative would be going down, okay? So that can be one of the variables in our actual equation. We don't really know. We might be told what our change in distance is, and then we can plug that in. But our change in distance will be equal to our initial velocity. So that's v with a little naught on the bottom there. We call it v sub naught or v naught. That's just your initial velocity times time plus 1/2 of your acceleration times your time squared. Okay, that's the biggest deal right there. That's like the master kinematics problem, okay? A lot of times, this is the expression you actually use. And when you actually look up kinematics problems, you'll see like a chart where it'll tell you, you know, if you have these variables and you're missing these ones, then this is the equation you use. And those kind of things are good to have. I would suggest, like, you know, just look up kinematics equations really quick at some point when you're doing these if you need to. This is the master one, though. This is the main one right here. You can see that, let's see, there's certain versions of this equation here that we can use. So let's look at this. Like, what if we have acceleration equals 0? So if you have acceleration, you have a situation where you have no acceleration acting on this object at all, then the equation reduces to your change of position is equal to your initial velocity times time. And that's probably the first kinematics problem everybody is introduced to before you even know what the hell a kinematics problem is or anything like that. Your velocity times your time is the distance traveled, right? Or you can divide that equation by time on both sides. So you have your distance traveled divided by the time it took you is your velocity. Okay, so on and so forth. That right there is one that we've all pretty much worked with at some point or another. That's for acceleration being 0. Of course, if you have something like, if you have your initial velocity equal to 0, then you can see that our change of position will just be 1/2 acceleration times however much time squared. Cool. Another thing to note about this equation here, this delta x equals v naught t plus 1/2 at squared, is that this is a quadratic, right? Actually, it's kind of it looks like a parabola, right? It's basically it's parabolic in t. Oops, in t. So what that means is usually when we deal with a parabolic function, we're dealing with x and y, right? So you have your y being the vertical, and you have this parabola going opening up or opening down or opening left or right. This thing's a parabola with the independent variable being t. So if I was going to plot something, I would have something like, I don't really care about negative time, but I'd have a plot that looks like this. This would be your position along the vertical axis, and this would be your time along the horizontal. And because this thing has a linear term in t and a square term in t, this thing would actually start kind of looking like a parabola. So what that means is, if I wanted to start from time 0 down here in the bottom left corner and move to the right, I would expect if this thing was like, let's just say we're starting from the 0 velocity, right? So things starting from rest, and it's the cart that we're talking about. And you start at the top of the track, and you just let go, and then it just starts rolling, and it starts increasing its speed a little faster, going a little faster, going a little faster. It's accelerating down the track, right? Its distance that it travels per unit of time is increasing because its velocity is increasing, right? So as this graph here travels to the right, it's going to get steeper and steeper and steeper because the amount of position changing per second is getting larger and larger, right? So you expect it to go along and steadily increase at the rate, increase the rate at which it's increasing, increase the rate it's increasing. And you see here, I kind of drew what almost looks like a parabola, right? It's like half of a parabola. You can imagine the other half is over here somewhere. Okay, but we don't care about time less than 0, obviously. So we just look at the positive half here. But that's what we would expect for a position versus time graph when something's accelerating, right? The thing I want to talk about, this graph becomes really important, and this is kind of like what we're going to focus on, is if you're making these measurements and you took this data here and you had, this thing accelerating as, its distance is increasing with time, and the rate at which its distance is increasing also with time, you can see that this thing's going to get steeper and steeper and steeper. Okay. I want to talk about the slope of this graph here. So I'm going to go ahead and make it again on the next page. So we have something like, probably like that. Here's my X, here's my T. Okay. So that's something I want to talk about here, and it's the slope of this thing. So what is slope? All right. Slope is going to be rise over run, right? Rise over run is usually like the oldest version of slope that we remember. In this case, what is rise and what is run? Well, rise means up and down, run means left and right. Up and down is our X, right? So slope would be like a change in X over a change in time. That's rise over run for this graph, right? Okay. So for this plot here, what we're basically, one of the things in physics that the reason I'm switching over to slope now is really I want to talk about these graphs, right? And this is kind of the first thing to do is talk about slope. And what I really want everybody to know is that in physics, if you're given a graph, one of the first things you do is you look at the slope. What the hell is the slope? That's what you want to know right away. I look at this graph here, I have position versus time. I look at the slope, it's change in distance over change in time. My slope is my velocity. Right, so you can see that here because I have rise over run, I have my change in X over change in time. That's like meters per second, let's say, and then there's your velocity. So you can see that my slope is my velocity in a given point in time along this curve, which you have some physics, or you have some calculus background, so you kind of see what I'm coming at here. You take the derivative of this graph and you'll get a graph of the slope of this graph, right? It'll be how the slope changes with time here. But anyway, so here we have it. So our slope is our velocity, and you can see that at some time like t1 over here, our slope is not so large, right? Because horizontal is 0 slope, and then vertical is an infinite slope. So here we're like almost horizontal, right? We're just a little peaked up a little bit. So this is some small slope, and then over here at like t2, you can see that our slope is much bigger, right? We're much steeper right about here. Okay, so our slope is increasing, which means our speed is increasing. And that does make sense, right? This thing's accelerating down a track, so we should expect its speed to be increasing. Okay. Let's look at the graph of this thing's velocity over time. Once again, this is just the cart that we started from rest and we let go, and it's starting to accelerate down the track, right? So again, this thing started from 0 velocity, and so this thing's going to start from 0 down here in the bottom left corner. The thing is that our velocity steadily increases at a constant rate, right? So we're accelerating at some constant acceleration, so therefore our velocity is increasing at some steady constant rate. And what we actually expect is a straight line with some positive slope, right? With some positive slope that doesn't change. Hey, I've just been given a graph. Someone just gave me a graph, so I should actually check out what my slope means, right? So, okay, let's see. Slope here is going to be rise over run, right? Rise is my change in my y variable, which is velocity. So I have change in velocity over run. So rise over run, right? And run here is going to be my change in my horizontal component, which is going to be time. So I have change in time. And let's see, what the heck does that mean? I have change in velocity over change in time. So that's like meters per second per second. Oh, that looks familiar. That right there is acceleration. Okay. So what I found was that the slope of my position versus time graph, which is here, maybe I should label them. My slope of my position versus time graph is a velocity, and the slope of my velocity versus time graph is an acceleration. Okay. Now we're going to get to see basically how a lot of science is done. A very simplified version of it, but that's what we're going to see now. Okay, so we have these two graphs. Cool. What are they useful for? Basically, I wanted to talk about what these graphs mean, what the slopes mean, because what you're going to do next is, well, for the lab, is you're actually going to look through these two graphs that you're given. You're given a position versus time graph and a velocity versus time graph, and you're given an equation that fits the graph. Okay, so here's how science works. Okay, well, that's bad. Here's science. All right. So what I mean is, a lot of times in some given experiment, what you'll actually do is you'll take some data from some run that you've made, some trials, and what you'll try to do is you'll try to use a fitting program to fit that data to some kind of expression, some equation, right? So you're given data. Usually you find it, but in this case we're given it. And it's, if you put the data onto a plot, it looks like that, okay, like we were doing before. Okay, cool. So this is your data that you're given. You use a fitting program. Fitting program to fit the curve to an equation. The reason why we do this is we take, a lot of times physicists find some random data and they try to plot it to some expression. It's usually an exponential or something like that. And we try to actually see what's happening. And then if we can find a valid form of an equation that actually explains this data, then maybe we can try to use that equation to explain the physical phenomena that are actually happening in the problem, in the research, whatever we're doing, the experiment. Here, that's kind of what we're doing, but like a nice little simplified version of that. So what do we do? In the lab, traditionally what we used to do is you would have this cart, you'd have it let go and it would accelerate down the track. You would actually, you'd record the data, which is how long it took to make its trip down the track and how far it was going. And actually it tells you how far it's gone and its current velocity and the timestamp for each, I think it records every 50 thousandths of a second or something, like, depends on what you set it to. And so it makes this data, this curve right here is what you'll see output from the program. You'll see distance along the vertical, horizontal is time. You'll see that you see these little data points, and they're basically just a bunch of little points. They're kind of like, sometimes they fluctuate a little bit because there's a little error, but you'll just see them going up like this. And then what happens is the software itself goes, okay, I see some kind of curve there. And then the user, you go in there and you tell it, I'm expecting there to be some kind of parabolic curve. And you tell it, I want this curve to fit some equation that looks like, your vertical is equal to some number times time plus some number times time squared. Okay. Now I'm being a little vague here, but that's essentially what the program's doing. You tell it, hey, I expect this to be of a parabolic form. Okay. I expect this thing to have it almost looks like an exponential increase. It's some kind of parabola. It's like half a parabola, right? So I expect it to have this form right here, right? This is what you expect it to do. The computer says, okay, I expect that. I know you want that. So I'm going to go ahead and see if I can make it fit, right? and it'll vary these different numbers. It'll change these over and over again until it finds one that fits. Okay, and essentially that's what happened. Now, in our actual experiment here, what happened was the computer found that x of t, so this is the function that we're in the question here, x of t is equal to 0.8515 t squared. Okay, that is the first plot on this lab. I'm actually going to pull it up right now on my computer to make sure that I'm looking at the right thing here. Yeah, 8515, yeah. Okay, so this is what the computer found, right? The computer found that first number in front of the single power of t, it was like, okay, that seems to be 0 because this thing's starting from 0. So the best fit the computer found was to set that equal to 0. And then the best thing the computer could do to match a line to that curve of data, those little data points that I drew on there, was it found that number in front of the t squared should be about 0.8515. Okay, so that's just the computer just plotting just trying to fit the data, just trying to do whatever it can to make the data fit in some parabolic form. Okay, now why does it help us? That helps us because we expect this thing to be of this form, some number times t plus some number times t squared. That is actually this equation I gave you in the very beginning, right? That's this kinematics equation. This is what we expect because we're trying to find a change in distance over time, right? And this is our distance versus time graph. So we're expecting it to have this form. This is the form that we want right here. Okay. Oh, I see the chat's got some questions. Yeah, okay. And then for table 1.1 in the lab is asking for average or initial acceleration. Table 1.1. Oh, so that's the thing. Okay, so average or initial acceleration. The thing is, we're just going to head and we're sliding down this track, right? The acceleration is going to be constant the whole time because the acceleration is really due to gravity, and it's due to gravity acting on a certain angle. And since the angle doesn't change and the planet that we're on doesn't change, the acceleration doesn't change. So we'll have a constant acceleration the entire time. So don't have to worry about like averaging or anything like that. To answer a question that I missed earlier on. But okay, so we're almost there. So being the clever little physicists that we are, we decided that we're expecting it to have this form of this kinematics equation here. So we tell the computer to fit it to that form. It does, and it retrieves this x of t is 0.8515 t squared. What does that mean? Well, if we expected that to be of the form, delta x is equal to v naught t plus 1/2 at squared, and we got that our x of t, which is just another way of saying it really, was 0.8515 t squared, then we have a pretty damn good guess here that this 1/2 of a is probably 0.8515, right? Now, if you're looking at what I'm doing here, I'm basically kind of giving away the first part, table 1.1. You can see that, we tried to fit the data to this curve here. We got that the computer found that 0.8515 t squared, again, that's a typo there, kind of is the best way to describe that curve. And we know that it's looking like this expression here, right? So then we just go ahead and equate the two. Well, looks like our single power t was multiplied by 0 in front, so this thing went away, so we don't have to worry about that. And then the 1/2 at squared is the only thing that's left. So it must be that the 0.8515 t squared is 1/2 at squared, right? So we can go ahead and say this, and then we can say that our acceleration is twice of 0.85. I think it's 1.0 or 1.70 something. I actually don't have my calculator. I should get that. So cool. So we found that A is 1.703. Right? Pretty cool. Told you I'd make it easy for you. Essentially the answer to finding some of the data right there, but that's not the whole. Anyway, whatever. So we did it. We found some acceleration. What did we do? We did science. Okay, how science works. We take data. We try to fit that data to a curve. The best fit that we have, we actually measure the best fit through chi-squared and other statistical analysis. But we find the best fit curve, and then we use the parameters of that curve to try to describe the physics actually happening in the problem. So the thing is, Daria, the acceleration normally would be 9.8 meters per second squared, except we're at an angle. So it turns out that when you're on that incline, right, you have some box and incline. You're trying to, if you're going to accelerate down the incline like so, turns out that gravity is acting straight down like that, right? This is whatever angle you're inclined at, which will actually turn out to be the same angle that's right here. And turns out that the bottom, so this right here would be mg, and then the bottom of this triangle, oops, mg, look up. This will be the normal force, so on. Oops, I drew my angle in the wrong spot. God dang it. Okay, again, but shorter. Boom, boom. Going down the incline, okay, mg acts straight down. This is the normal force. This is the force we actually care about. The theta is actually right here, my bad. Theta is right here. Theta is in that little corner there. This is mg right here. And it turns out that if I want this force, which is actually the same as this force, it's just placed down there, it's mg sine theta. That's going to be like the force accelerating you. And so that's why it's actually not 9.8, because we're at this angle. So, you know, the angle could be whatever it is. Like, if I don't care about if I don't care about the force, I don't care about the gravitational acceleration, x is g sine theta equals the acceleration of the system. And then if so if theta was like 30 degrees, then it'd be 9.8 sine 30, and we get something like 4.9. So it must be less than 30 degrees, right? Maybe it's like 9.8 sine 15. It's less than 15 degrees, right? Sine 15 gives us 2.53. Okay, anyway, but we'll cover that kind of stuff later on anyway. But that's a quick little explanation as to why it's not 9.8. Just because we're at that angle there. Anyway, so I erased that because it's really not important for now, I guess. We will cover some more of that kind of stuff in the future. And it doesn't really pertain to this lab so much, so don't worry about it. Anyway, shoot. Need this to be full screen. Okay. So that's the position versus time graph right there. There's also a velocity versus time graph, and that actually gives us another kinematics equation, so we should talk about that too. Another kinematics expression is there's several of them, but we are only going to talk about two for now. We'll maybe come back. We'll come back to some more of them later on, but for now, the number we're going to talk about is your velocity is equal to your wait, which one are we doing now? We're doing some initial velocity plus acceleration times time. I believe that's the one we're using now. Yeah. So this here is another kinematics equation, another very important one. You can find your final velocity, which is usually what we call this. Your final velocity is equal to your initial velocity plus your acceleration times your time. That'll give you, you start at some initial velocity there. Acceleration times time, that's meters per second squared times seconds to give you meters per second. So that term with acceleration times time gives you another like velocity measurement to add to your initial velocity to then tell them what your final velocity is. Okay, so that's the other form of the equation. That's the form that we'll be using for this lab. Like I said, there's some other ones, but let's worry about those for now. Now you can see that this velocity versus time simulation, figure 2.1 of the lab here. Same kind of stories before, right? So what happened was we had some data. This is from the cart. The cart's measuring its velocity as it rolls down. So it's measuring its velocity every 50 thousandths of a second or whatnot. And what it gets is this. It gets a bunch of data points that all kind of trend towards this, like, maybe there's a little bit of fluctuation in there, but that's about what it gets, right? If you can see my screen share here. Yeah. So that's essentially what that's the data that you get, right? And then you tell the computer, hey, I want this to be a linear fit, because you're expecting it to be this form, and that's linear. So you tell the computer, tell computer, expect linear. So this would be like the computer trying to plot the data right here. This would be like the line the computer plots to try to match the data. Next page here, I'll just say that, the computer finds, let's say that the computer's fit is, let's just say, it gives some, well, it won't even give you it'll just say, like, f of x is equal to 1.703x. That's what the computer will see, right? Just the basic function. Okay. But we know that this is actually supposed to be the velocity. So this thing we can expect, oh, well, this is f of x is my y component, right? So this is actually velocity. And then this x here would actually be time, right? And this is the expression that I actually get from the computer trying to fit to the data that I got from the experiment. Okay. Like I said, the computer just sees, my y variable, my vertical variable is equal to some number times my horizontal variable, and I'm like, oh, I interpret that as, oh, that must be my velocity is equal to something times time, because I expect it to be of this form, right? I expect it to be like this. Okay, my final velocity, that's v here, and then this v naught. What the heck is v naught here, right? Well, looks like it must be 0. And then I say there's a question: is the initial position for the first graph just 0? Yeah. So since we start this cart from the top of the track and we just let go, we just assume that the starting position is 0. It's usually more convenient to do it like that. You can actually tell in any physics problem, you can make any position 0. So you can make, like, the bottom of the cliff, like after you've fallen down, you can make that 0, so that the whole time you travel, you're doing like a negative change. Or you're starting at some, like, positive value and then going to 0. You can start at the top of 0 and then go to a negative value. You can do whatever you want, really. But yeah, so we're just going to say it's the top of 0 for you. Okay, so I expect the expression to look something like this: Vf is equal to V naught plus acceleration times time. And it comes out that the computer finds that the best way to fit this is to say 1.703 times time. Okay, well, that must mean, let's see, that means, so that implies, what does this imply? This implies that V naught must be 0, right? Because this term has no t on it, and there's no term here without a t, right? It's just 1.703 times t. So this also implies then that expression is the AT, right? And so this must mean that A is the 1.703. Okay, which that actually agrees with the last plot, right? Because it was 1/2 of A was 0.8515. Double it, you solve that expression for A. Go back here. This 1/2 of A is equal to 0.8518. So then you solve it for A and you get this thing here. Okay. Well, this other graph on the next page or whatever is actually, if you actually look in the lab, this table 2.1 or figure 2.1 or whatever it is, it's the same data. It's just the velocity over, it's a velocity at any given time rather than position at any given time. So we should expect the same acceleration because this is actually the same run. It's the same experiment. We didn't run it again. It was literally the same run, which is what we actually do in the lab. This is the part where you'd be setting this up and doing the runs, and you'd have it. You think you run it like 5 times an average or something, but you would have a velocity versus time and a position versus time from the same release and drop of the cart. Okay, so we'd expect that to be the same now. Let's see. So essentially what this lab is doing is it wants you to understand what these plots mean. It wants you to know basically everything I just told you. It wants you to understand that this displacement or change of position along the vertical axis here, and then time along the horizontal axis, this position versus time graph. If you try to match the curve, that you're going to get this form of this this kinematics problem. Delta x is v naught t plus 1/2 at squared. See another question here. So hold on. Our table 1.1 and 2 asking for us to display the variables. Could we include the specific values as well? Okay. Display the variables as in like v equals something. Inside where it says initial velocity and you have to fill in the box, you don't have to say like v naught equals whatever. You just put in the value. Put in, see, they have the units already in the boxes too. You see acceleration meters per second squared, and then the second table is acceleration. Oh, it's acceleration v over t. Essentially, so what I just said here on this last page was that, if we get this plot of v equals 1.703 t and we expect it to be of this form here, this kinematics question here, then that implies that our v naught must be 0 and then our acceleration must be the 1.703 in front of the t. So for Daria, essentially, yes, you take that expression, divide t out of it, and that 1.703, that's what's left over. That's one. And then I see another, okay, so if we plugged in t equals 0 for time 0, then initial velocity would be 0. Yes, exactly. So, and we would expect that. So plug in time 0 to this v equals 1.703 times time thing, you get v equals 0. So at time 0, your velocity is 0, which we expect. If there was a constant in there, so if it was 1.703 t plus some constant, and I plugged in time equals 0, then I'd be left with that constant, and that would be my initial velocity, and that would then follow this form here. Right, we'd have that v naught plus at. But seeing as it's just 1.703 times t, there's no other term. This must mean that your initial velocity is 0. That's essentially it. The other thing you guys have a little bit of calculus background, so I want you to know that if you take this position versus time stuff and you take its derivative, you retrieve the velocity versus time stuff. Right? If I look at these two graphs, like one on top of the other, this graph does this graph does that. You know what, actually, let me make room for 3 on here. Another important concept in physics. Here's my position versus time at the top, my velocity versus time, and then my acceleration versus time, right? Okay. And remember, this is, going down here, it's the derivative, right? d dx, essentially. d dx. Well, d dt, I should say, but whatever. Okay, I'll give it d dt. Just a little reminder of the calculus that's at work, and eventually you'll get to use calculus in your physics again. Yeah, so for both tables, the acceleration is 1.703. And like I said, that's because it is the same experiment. We did one run where we dropped this thing and it went down to the bottom of the table, and that was it. And we recorded the position at every given time increment, and we also recorded the velocity at every given time increment for that same run. So it was like one run, we recorded 2 different data points for each time value. And so we should expect that the values we retrieve from both those graphs should agree with each other. Question 3 asking, there's dollar signs. Okay, yeah, the dollar sign thing, that's a LaTeX So like this thing was probably done in LaTeX or some other form or something, and they tried to like make A of t some fancy other, doesn't matter. They probably tried to use the equation environment in LaTeX or something. But write down the acceleration versus time. So actually, what I'm talking about right here is actually going to help you with that. So you see x versus time gives you this parabolic curve, right? Velocity versus time gives you this linear curve, because this is your velocity over time. Your velocity should be linearly increasing. Your position is like parabolically increasing. What's my acceleration doing though? Well, my acceleration is constant, right? Because I'm at a constant angle, and gravity, the Earth's gravitational acceleration doesn't change. So my acceleration down the actual track shouldn't change either. And so that's why you get this horizontal line. But you can see here that the derivative of the top graph is the middle graph, and the derivative of the middle graph is the bottom graph. So what should be our acceleration with respect to time? It should just be a constant, right? If I don't want it dependent on time, right? If it was dependent on time, then I can put in time equals 2, and I would get like 2 times something or whatever it would be. And my acceleration would be changing with any given like time step that we're on. But yeah, okay, I see. That's exactly what we have is this is constant. And so then A sub t or A of t should just equal 1.703, and that's it. And it's kind of strange to say A of t, but it's really just to show that, normally it'd be a function of time, but this is not dependent on time. If you look at number 4 here, okay, hold on, one more question I see. So for number 4, yeah, okay. Number 4 of the question portion, would the force be generated by, question portion. We observed a constant acceleration of our cart down the track. This implies that there was a constant force being applied to the car. Think about it equals ma. What was generating the constant force? Gravity, exactly. Again, this is like the inclined plane problem, which we'll talk about eventually. But some object sliding down like that, and then you have your normal force and mg. And then this 9 degrees here, pretend that there is mg sine theta. Question number 5, since data is recorded after 10 centimeters, are we able to say that those 10 centimeters are negative, or do we just forget about them? Data is recorded after 10 centimeters. I don't actually see what you mean by recorded after 10 centimeters. Looks like the recording starts, if you look at, so hold on, I'll stop my screen share really quick. If you look at this graph here, you can see that the thing actually appears to start from basically 0, right? Your graph is, we can go ahead and just say it's 0. We actually, yeah, as far as the position goes, it looks like it's starting from the very bottom of the, very bottom of the line there, like right there at the very bottom. It's 0 position to start. Let's see, maybe. Oh, okay. You went up and read the setup. Yeah, it's don't worry about that stuff. Yeah. I usually actually I don't let that like become an issue, because when I do this lab in actual like in person, I have everybody wait until it starts recording, and then they drop the cart, just so that it starts from 0, or it starts relatively from 0. So that's how I usually have people handle it. But yeah, so. Okay, so as far as the negative, is it possible using the experimental setup to get a negative position value in the position for semi-graph line or not? Sure. I mean, it's totally possible, because it's like I said, it's like I guess this part I forgot. I didn't really answer this part. Yeah, so it's totally possible. It really just depends on where you decide to put your 0. I could put 0 on the bottom of the graph, or I could put 0 like at the end. Like when I hit the bottom of the track, I can make that 0. And I can make everything else. I can start at like negative whatever it is, right? Negative 80 centimeters or something. So, is it possible using the experimental setup to get a negative position value on the position versus time graph? Absolutely. It really just depends on where you decide to say your 0 is, which is really completely up to you. All that really matters is that you're consistent. But I think I've basically covered everything you need to know that we should talk about here. Yeah. The biggest thing that I want you all to know is what I was talking about in the notes here, which is basically that it's this concept here. You know, it's that the derivative of your position versus time graph is your velocity versus time graph, or basically that the slope of this is this, and that the slope of this is this, right? That's kind of going back to those calculus concepts right there. The derivative being, you know, the derivative of some function being essentially a function that's telling you the slope of the original function everywhere in space. That's the biggest concept here to write home about. That and using these kinematics equations. That and I guess also understanding a little bit about how science works, which is basically we're given some data and we expect it to be of some form. We tell the computer it's going to be of this form. It does this little boop, 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 you know, it does a best fit parameterization. It changes the parameters around. It checks something called the chi-squared every time, which is another complicated thing that we're not even going to get into, but it's basically a goodness of fit measure. Because we have to have some kind of, you know, we have to have some kind of language for how good is this fit. It can't just be like, oh, looks pretty good. We can't just do it by eyeball. It has to be some kind of mathematical structure for it, and that's called a goodness of fit or a chi-squared. The computer runs that every time until that goodness of fit number gets smaller and smaller and smaller, and the smallest goodness of fit, like the really closest fit it gets, it sticks with that number. And the numbers that it was changing was this 0.8515 thing. It was just changing that around a whole bunch until it got a really good fit, and then it stopped and it crapped that number out, and we're like, oh, cool. That must be of the form, you know, delta x equals whatnot and so on and so forth. There it is. You know, v naught t plus 1/2 at squared. And so that must mean that 1/2 a is 0.8515. And that's how science is done, essentially. Same thing happens over here with our velocity one, right? We know it's going to be v naught plus at. The computer tells us, hey, it's 1.703x. Oh, so that means it's 1.703t. So it means a is 1.703. Okay, I'm going to let you guys take a look at those questions really quick, and I'll be right back. Go ahead and just ask anything in chat. I'll be right back, okay? Oh, I see one more thing before I leave. The first two questions are just equations of the graphs, right? Go on. First two questions are just the equations of the graphs, right? So explain the difference between speed. Oh, first two questions, you mean the analysis section? Yeah, so essentially they just want you to like see how it's written. Equations are written on the graphs. They just want you to write them again, but in the form of these kinematics equations. So like write down y of t using the coefficients. So just like, you know, instead of having x's and stuff, you're going to have like, you know, y of t is equal to, well, this time it's just going to be 0.8515 t squared. And then, you know, yeah, it's pretty silly. It's literally just like you're going to write it down again. But they want to make sure that you understand that equation's fitting that kinematics expression there. And then it's 1/2 times that. Weird. Yeah. Yeah, and Daria, yeah, what you said is true as well. Oh, you were answering them. Okay. All right, I'll be right back. Okay. How's everyone doing? Okay, so going back up here to answer any questions. Who's up for number 2 analysis section? So number 2 analysis section, rather than the equation v of t using the coefficients recorded in table 2.1, essentially, you say your initial velocity is 0, right? And your acceleration is that 1.703. So then you can just write v of t is equal to 0 plus 1.703 t. That's literally all I want. Just understand that you know that fit the computer generated is actually corresponding to this v of t expression for kinematics. Forget about the number signs around the a of t. It just means like, I just want you to write what a of t would equal. Like, what's your acceleration as a function of time? You mean the other number too? Oh, what happens to the speed and position functions when acceleration is constant? What happens to the speed and position functions when acceleration is constant? That's a very vague question, right? What happens to the speed and position functions when acceleration is constant? Well, our acceleration was constant, right? So yeah, it's essentially got to be asking about the shape. And if you look at the screen share I have going right now, the top graph, that's our position. Middle graph is our velocity. You can see our position is parabolic. Middle, the velocity is going to be linear. So when acceleration is constant, we have like a parabolic form, and we have like a power 2 quadratic. We have a quadratic form, I should say. We have a quadratic form. Yeah, I'll have you know I did not write these questions. So I don't know anything else I need to mention. I think I already mentioned everything I need to mention. There's some people that weren't here right in the beginning. I'll make sure you're here now. Andrew, I see you. Marissa, I got you. Who else? Okay. I can get these to be a little weird because like the way what they're asking for is for number like analysis section number 1 for like Emily there. It's simpler than you might think is what I was asking for. So okay, from table 1.1, we got so initial position, initial velocity, and acceleration, right? Number 4. Compare the answers found from equations questions 2 and 3. Oh, okay. So yeah, this one. So compare the answers found in questions 2 and 3. Write down general statement that relates to velocity and position curves. Hold on. Are the graphs separate, or is the second graph referenced to the first graph? The second graph and the first graph are from the same run. So they're different graphs, but they're like of the same data, essentially. Let's see. But okay, before I move on. So number 4, compare the answers found in questions 2 and 3. 2, if you could, I'm gonna go ahead and do my screen share here. On 2, you can see that you have some, Jesus, turn that down. Okay. We have some V of t is equal to 1.703 t. And then we have, for number 3 on the analysis, we have A of t, and that should just be, which some of you already done this and some of you, okay, 1.703, right? Okay, so what is the relationship between 1.703 t and 1.703? And depending on how confident you are with your calculus background, exactly, derivative, right? So yeah, d dt of v of t is equal to a of t. Perfect. And then Marissa, same data, got it. Yes, okay. Yeah, it's the same data. It's like this, we just did like essentially one run, we let it go down the bottom. The computer measured the velocity at every point in time, or I should actually say this. They can actually just message this to you. But yeah, so velocity at every point in time and position at every point in time. Yeah, so if you're done with the lab, submitted it, you're good to go. I already got you down. There's only a few people that are missing, and 2 of them showed up, and 2 of them haven't been here the last few times. So, yeah, because you're good to go if you finished. Once again, these notes will be up later, and then the recording will be up later for those of you who still want to look at back or anything. And I believe we have one new guy here, Sultan. If you can hear me, you are just don't be afraid to ask any questions you need or anything like that. Please email me if you want to, like, I know you just joined the class, so if you want to like get any extra information, go back on anything we did before, or for whatever reason. I'm not really expecting much, before you joined, but you joined this week, so just see. Were you here last? I don't think you were here last session. No, you weren't in the class yet. Yeah. Okay. So yeah, just feel free to you can private message me, or you can chat openly, everybody, whatever. If you need any help. Yeah, I should probably also mention again, also for you, Paul and Hilda too. I am recording everything, so hope that's okay. Recording it for everybody just to watch it later if they need.
My question is, on your view, can you see the interpreters? Is that getting recorded as well, or is it just your shared screen that's getting recorded?
So I think it's whatever Zoom sees. So I don't know. That's the thing. I don't actually know yet.
Like all of the screens see different things based on how every individual, depending on their device and how it's set, whether they have it a gallery view or speaker view, or. But I'm asking you because you're the one who's recording. What are you seeing on your screen?
Oh, well, what I see right now is I see participants. I see you and Hilda on the top, and then just a couple of the people with their cameras off, and then I see what I'm sharing on my tablet. So yeah, in the last two videos, you can see you guys, and if that's the problem, I can totally remove them or something. I'm not too worried about that. But
no, that makes it easier because that way, if she wants to review it, she doesn't have to request an interpreter every time if the interpretation is recorded. The other question I have is the size of the space. There's a bar that, depending on how you have it set up, either on the top or the side,
yeah,
you can expand it. We're large enough that we can be seen. That's all.
Okay. I actually, let's see. I don't know. Oh yeah, I could do like that. Well, yeah. See, I'm not sure yet. I have to watch this video, see how it looks. The thing is, I am sending it to the SASC people. I think the closed captioning people. So they're gonna in a couple days. She says a couple days for each one, but she's gonna send the link straight to Marissa, so she'll have closed captioning too when she looks over the videos again. So that'll help.
Awesome.
Yeah, as far as the video thing, I don't know. We'll see. I'm gonna open this up here.
What it looks like, I could tell you if the interpretation is visible well enough or not, or maybe Marissa can even share that.
Yeah.
Let's see. It is kind of tiny. Yeah, it's tiny unless I max screen it. But then if I max screen it, all I can see is you, and then the notes are really small. So I'm not sure. I'll probably just leave it like this.
Might depend on what device you're using, but I know with mine I can just slide it, and I usually try to make it so that the thumbnails take up about roughly half, and then I can still see your.
I see what you're saying.
You can slide it across or do the view option up at the top.
So it's in side-by-side mode.
Yeah, I kind of got me in the spot here. I'm not too familiar with some of the features here.
Just trying to make the recording as accessible to her as well.
Side by side mode. Okay, I see. Side by side mode. And then maybe I can like set a focus on. Let's see.
You just slide that side, like on mine, which I could show you my screen right now, but it's not enabled. But the notes are still very legible. But
Oh yeah, I see. Okay, I got it now.
slider.
Yeah, I got you taking up half the screen, and then I got notice on the left side. Okay, that works. Yeah, that's okay. That's good. That's pretty good. Let's see. Until to stand. Okay. I believe I actually was able to make it pin the video so that it should keep you, Paul, on like the side there.
The only problem with that is each time we switch, you'd have to switch the pin.
That's true.
When it's Tilda's turn. There's only 2 of us on here at a time, so I think it's fine just to leave it in gallery mode.
Okay. All right. Okay. Okay. Yeah. Here, let's see. I'm gonna make a very cheap hack of showing you what my screen sees. Oops. Okay. No, I can't see it. But yeah, half my screen is the notes and the other half is the gallery view. I can make it like half like Paul, but then I can't see Hilda, so this is actually how this works.
If you also click on one of those screens where the video's off and say hide non-video participants, it'd only be 2 of us on the screen.
Oh, okay. Hide non-video participants. Ha! All right. So everybody gets to look at my pretty face and yours. Okay. Let's see. Low tech. Boom.
That's what mine looks like.
Cool. Awesome. Yeah, that's good. Yeah, thanks for the tip there. That's actually looks pretty good. This is my first time, like, you know, dealing with the whole recording and everything. Like last semester was very disorganized, but this time try to make it a little better.
Then you have the added complications of the interpreters.
Right. Yeah. Okay, what are we doing? I just put AFC equals 1.703. Yep, perfect. Yeah, just ignore the, yeah. It's actually there because they probably tried to LaTeX this document, and when you LaTeX something and you want to make a math environment, you have to put a number sign, then the stuff, and another number sign. And it looks like they did 2 number signs by accident. Yeah, this, yeah. Yeah. Question 1 in the analysis is just the position function, essentially. They just want you, I mean, it's kind of goofy, to be honest. Because your answer in there is literally going to be like copy paste what you have up there, except for the time squared, right? For the x of t equals 0.8518 thing. Yeah, exactly. I mean, you could make it like whenever you get a goofy question like that in physics, go ahead and enter all the values, even if they're zeros. That sometimes helps. So, like, say x of t equals 0 plus 0 times t plus 0.8515 t squared. That's just a good rule of thumb whenever you see some silly question like that. Um, okay, 1 second. Let's see. Hold on. Okay, let's see. So your question is question 2. Okay, so if acceleration is constant, then it's the slope of velocity. Well, acceleration is always going to be the slope of your velocity graph. That's always going to happen, even if it's not constant. So you can get some weird graphs. But essentially what's saying here, what happens to the speed and position functions when acceleration is constant? It's kind of like another silly question, which is basically like, it's more obvious than you might think it is. They just kind of want to know about the general shapes of these graphs when acceleration is constant. If you look at my screen share here, you'll see that the top graph there is like it has a quadratic form, and the middle graph, the velocity versus time, is linear. And that's what you would expect when you have constant acceleration. You expect that shape to those graphs. That's essentially all it's asking for. Okay, number 1.
Do we just describe each graph?
For which part?
Like I know it's the shape, but like, do we for each of the 3 graph, do we just describe?
Do you mean like for question 2?
Yeah, for the relation of speed and position.
Yeah. So what happens to the speed and position functions when acceleration is constant? Yeah, there's basically just when all you want to really say there is that when acceleration is constant, we expect the position graph to be quadratic,
Okay.
and then the velocity graph would be linear.
Okay. Okay. Thank
The
you.
thing is, if our acceleration actually had like some function of time, then that would throw another time value. Like when we have that v is equal to at thing,
Mhm.
that would actually become like v is equal to like something times time squared. Let's say if there's like a power of t inside of a, and so we'd get some like non-linear thing. So basically, because acceleration is constant, our velocity versus time is a linear graph, and then our position versus time is quadratic.
Oh, okay, I get it now. Thank you.
Yeah. Class on.
Are you in class? You're not teaching it?
I'm trying to tell you, I can hear you. Yes, I'm teaching.
Louis,
Yeah.
Marissa just wanted you to know that her screen shut down and it just came back on. So she's trying to make sure that she got all of your message.
Oh, okay.
Stand by.
When she gets it back on, I can paste everything I just wrote back to her again.
Okay, she'll let me know if she's missed anything and I'll let you know. She said, yes, she missed everything from her. She missed everything because her computer just shut down. I think she's on her phone now.
Oh man.
Yeah.
Okay, so basically tell her that I just did a bunch of just to open up the screen share so you can see what I'm sharing, and that's like lab 2 stuff right there. I'm gonna paste. I think I just pasted everything that I wrote back in chat, which is kind of like a description of what I just wrote on the.
Yeah, that might be.
I'll do it one more time just to make sure she
Yeah.
gets it.
She says, thank you. She got it.
Cool. Stupid notifications. Yes, 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 yes.
Excuse me, Professor. You mentioned that we could verify some of our answers with you.
Yeah, sure.
Should we message you them, or how would you?
Either way, I mean, you could type it in the chat just so I can see the number if you want, but like either way, whatever you feel comfortable with.
All right. Yeah. So for one, I just got that speed is a scalar, it has no direction. Velocity has a direction.
Mm-hmm.
And does that make sense?
Yeah. Yeah. So speed is just directionless, and velocity is speed plus direction. Exactly.
Okay. And then I said, well, I already asked you about question 2, so I think I got that right. I'm just describing the graphs as linear and then quadratic.
Yeah.
Question 3, I said that the slope would get steeper because you're covering more distance with the same amount of time.
Exactly. Yes.
Okay. And then obviously gravity. I mean, they're just pulling the cart down the track. With
Oh yeah, number 4.
number 4,
yeah,
right?
gravity. Yeah. Mm-hmm.
And then from this experiment for number 5, I was like, well, typically you could get negative position if it was me standing on the street, but for this experiment, the cart can't go any further back because it's already starting at the beginning of the rail.
Yeah, that's true. But the thing is like with the way this situation, the way this lab's set up, and how the cart measures, yeah, it doesn't really make sense that you'd have a negative position. But you could, if you want to make a negative position, just by, saying that your starting position is at positive 10 centimeters or something, and so that you start at negative 10. You could do that if you told the machine, like you can tell the cart to do that. So like,
okay, I got you. So I could have made halfway down the track 0.
Exactly, you can make the bottom of the track 0. You can make
Okay. Then my entire experiment would change. The initial velocity would change. Right?
Well, no, the initial velocity would still be 0. It would just, honestly, yeah, not much would change except for just what you call, like what position you call 0, what position you call 80 or whatever. It literally just, almost nothing would change. So, do you get negative position value on this position versus time graph? Yes, if you tell it that it's starting at some negative value. It's kind of a weird question. It's one of those questions where it's like, in this lab, like, no, the way we set it up, no. But I mean, theoretically, yes, I could easily make like one change and I could make it do that. So when it's something that's like, that's kind of like a more like creative question there. It's not really like if someone said that no, we couldn't, and if someone said yes, we could, I would kind of consider both of those correct answers. I want to see a why or why not. That's all.
Okay, yeah, initially I said no because it's the cart from the experiment explanation. It's starting at that little metal bumper.
Yeah.
But I changed it.
And that would be correct.
I changed it because I understand what you're saying now as well. So.
Yeah. Yeah, either way.
And then for the question 1 on the analysis, I talked to you about that as well.
Mm-hmm.
I put the position, which was 0, then velocity function, which is the 1.703 at t, and then the position function, which was 0.8515 t squared.
So be careful. So our initial velocity is actually 0, right?
Yes.
So we'd have something like this. If you look at my screen share, we'd have like y of t equals your starting position is 0, so it would say 0 that, 0 for why not, plus this would be 0 times t, right? Plus, and then this 1/2 at squared, that 1/2 a
Oh.
was actually 0.8515.
So it's 0 times t.
Yes.
Sorry.
And like, you can honestly leave it in this form here because that just shows me that you understand that your initial velocity was 0, and that your initial position was 0.
Okay, yeah, because I had that for the next one, which is where I'd have b of t equals 0 plus 1.7703 t.
Yes, exactly. Good.
The a of t is just it's just a number.
And that number is
1.703 meters squared. Meters per second squared.
meters per second squared. Yeah, I'm not too worried about the units in this, just because it's but you're correct. You should put units on there. That's good. Might as well. But yeah, that's it. That's essentially it. Compare the answers found. Did you understand the question 4 in the analysis section for comparing questions 2 and 3?
I was going to ask about that because I just went off of what you drew earlier about the slope of this is the slope of this is this.
Right.
So the position. So what I wrote was acceleration is the derivative of velocity v of t.
Yeah, that's
And then
exactly it.
Okay.
I would literally just if I just saw this, I'd accept that.
All right.
Because that's what you just said in math speak.
All right. I'm going to submit the one sheet of work I have with this Word
Okay.
doc, but there wasn't a whole lot of real work on this one.
No, I know this lab is more conceptual, and there's a little bit of work, but that's really
Okay. All right. I think that's it. Thanks, Professor.
yeah, of course. I will see you next week.
See you next week.
Mhm. Let's see now. Could I go back 2 slides before I show the R value? So 2 slides before the R value. So there's the R value. 2 slides before is this one. See who we still have here today. Got one more person besides the 3 of us. Hmm.
So you have to know how to use sine and cosine accurately, right?
Yeah.
Plus directions, the positive and the negative, right?
Yeah. And your unit circle. See,
Again, please.
the unit circle. Actually, I can draw that on the next page. There's a trick I have for that. But the whole thing with the signs, I should probably do this in a different one. Okay. The sign thing, you can declare whatever direction you want to be positive or negative. As long as you're consistent through the entire problem, it doesn't matter.
So just to be clear, the force would be positive, so that would it would go up
Well,
or to the right. I'm a little confused because I use that graph.
like this one. Yeah.
A minute.
Oh.
I thought that it would be negative force because of the hypotenuse.
So the hypotenuse.
Globe would be positive because no.
would go up, the length would go up. The length would be negative because it's going to the left, but it wouldn't actually be true. It would have to be positive because it would be squared,
Yeah.
and it would give you more of it would be negative. Those two negatives would be the positive. Right?
Yeah. So the magnitude of these vectors will always be positive. They're positive because you have a square of each side added up and then square rooted. So it's like you said, when you square the negative, you have negative and a negative make positive. So the thing is, you always want to have your
I'm
magnitude.
curious to know if the force okay, so I have asked her to sign a little bit slower. So I'm curious to know if that force 0.635 newtons would be going up northwest, kind of, instead of the opposite way, would headed south, east.
So this is the resultant. The resultant's going to be the the northwest one, because this is the sum of the two that I was given, which are back here. Like I added these two up and I got this one. So it really just depends on what the components are, right? It depends on what my Rx and my Ry are, right? So I can have Rx be positive or negative, and Ry can be positive or negative. If it was going to be southeast, my X would have to be positive, my Rx, but my Ry would be negative. It all depends on the vectors I was given. It all depends on F1 and F2.
Okay. Yes. Okay.
Now, there is going to be a vector. There's going to be a vector to the southeast. That's going to be my equilibrium vector, the one that I found right here, because it needs to cancel out the one pointing to the northwest. But I made this one. This one here exists, is already there. And that's just basically like, there's two ways to like show this problem. One, I can pull up and pull out a little bit like this, or I can just pull like, instead of not straight up, but somewhere in between. I can pull there with like a certain different force, and those two things are the same.
So that would be southeast.
Well, this one is the equilibrium vector is. That's the one that cancels out my resultant vector up here.
Okay. Yeah. All right. Got it. Okay. Thank you for clarifying that.
Yeah, no problem. I'll upload these notes.
Getting it now.
Sorry, go ahead. What was it?
I'm sorry. I said I really like. I have lots of questions. I'll be asking them a lot, and maybe getting some clarification and understanding it a little better. You know, the directions tend to confuse me. I know there's more work to find the magnitude and which direction compared to with regards to the vector.
Yeah, I mean, the thing is, I'm totally willing to answer all these questions and everything. So like, don't feel bad. Don't please ask away. The thing with this lab is I just want you to practice decomposing two vectors. All I really care, the equilibrium thing is, that's one part, but I want you to take two vectors, be able to break them down into their X and their Y components, add up the Y's, add up the X's, and then make a new vector. That's what I want you to know from that lab.
Great. Okay, thank you.
No problem.
I guess I'll see you next Monday.
Yep. And I'll get this thing uploaded.
Sorry about today. My alarm didn't go off. I got me up at 8:45 and I was trying to get myself together to get on there.
That's okay. You showed up.
There's no way for me to have a backup alarm because of the type of alarm that I need to have. So,
Right. Yeah.
okay.
All right. Have a good weekend.
I'm going to try and make it every week on time.
Yeah, it's okay. It's okay.
Okay. Thank you. Bye. Have a great day, everybody.
You too. Bye.